Welcome to another CHEM271 tutorial session. This one will be about carbohydrates. So specifically, we're just going to look at how to convert between a Fischer and a Haworth projection. So this here is an example of a Fischer projection. The Haworth projection, as we'll see in a bit, is the hexagonal ring structure of a carbohydrate. This is just looking at monosaccharides. So there's 4 rules that we have to follow in order to convert this Fischer projection to a Haworth projection. We'll also look at the opposite later, how to go backwards. But the main rules are, so for carbon 2, carbon 3, and carbon 4, just looking at the OH. So if we're just looking at this one here, example A, so this up here is carbon 1, this is 2, 3, 4, 5, 6. It's a hexose. So for carbon 2, carbon 3, carbon 4, OH, on the right, if they're on the right side, that means in the Haworth projection they'll be going down, and if they're on the left, they'll be going up. So this one here is right. So in this case, this will be going down. This one's left. So this one will be going up. Okay, same for this one. Right, it's down. Okay, so this is just looking at carbons 2, 3, and 4. So this little block right here. Okay, the next one for C5, so looking at the OH, if it's on the right, it's a D sugar. If it's on the left, it's an L sugar. So this one here is on the right, so this gives us a D sugar. So this is sort of the enantiomer, L enantiomer, or D enantiomer. Okay, so then the next one, this is, so these last two are mainly just for the Haworth projection when we're drawing it. So if it's a D sugar, this CH2OH on carbon 6 will be going up. If it's an L sugar, it will be going down. And then we also have to think about the anomers, which are alpha and beta. So anomers are, they are the same exact sugar, but they only differ in the stereochemistry of the OH at carbon 1. So the alpha anomer is the CH2OH, and the OH on carbon 1 are going to be on opposite sides. And the beta anomer is the CH2OH and the OH are on the same side, okay? So we are going to draw this one, and then we're also going to name it. So we've already figured out most of this, right? So now what we're going to do is draw the hexose. So we draw an oxygen here, and then we draw the 6-membered ring, like that. And then the way that we number this is 1, 2, 3, 4, 5, and then where's carbon 6? It will be connected to carbon 5. So we can start with that. We know that this is going to be a D sugar, as we decided. So in a D sugar, this will, the CH2OH on carbon 6, or the CH2OH is carbon 6. So in this case, it'll be going up. CH2OH, this is carbon 6. Okay? So now we have to look at carbon 2, carbon 3, carbon 4. We know that carbon 2, the OH will be going down. So we draw like this. On carbon 3, the OH will be going up. And on carbon 4, it will be going down. All right, so now we just have to look at carbon 1. So in this case, this sugar will be in the alpha configuration. So if it's an alpha configuration, the CH2OH and the OH must be on opposite sides, so that means this one must be going down because this is going to be opposite. So these two opposite. Okay, so this sugar is going to be alpha D glucopyranose. So it's the D configuration, it's alpha, and it is a pyranose, so it is a 6-membered ring, okay? It's also glucose, so that's where the gluco is coming from, okay? So this sugar here is D-glucose in this configuration. But when we add in these extra details with the alpha, this is what the name of the Haworth projection is, okay? So for this one, we're going to be shooting for the beta anomer. So in this case, we're going to do the same thing as last time. So this one, carbons 2, 3, and 4 first. So looking at this block here, this one is on the left, so this is up. It's on the right, so down. And this one is also down. Okay, C5. Carbon 5, this one is on the left, so this represents an L sugar. So, okay. Now, we know this is an L sugar, so we know this CH2OH is going to be down. This is also going to be a pyranose, so it's going to be a 6-membered ring. Okay. So let's first draw the CH2OH. So we know this is an L sugar, so this will be going down. Sorry, wrong position for that. Should be on this one. So if we number this again, 1, 2, 3, 4, 5. And then carbon 6 is here. This will be going down, CH2OH. All right, we know this is beta, so that means that the OH on carbon 1 will have to be on the same side. So I should mention that this is C1. So this will be going down, right? Beta anomer, they have to be on the same side. All right, now the rest of this is fairly straightforward. We know carbon 2, this one's going up. Carbon 3, down. Carbon 4, down. And that's it. So we know this is a beta sugar. We know this is L. And we know this is a pyranose. In this case, this is galactose. So this is galactopyranose. All right, and this sugar here is galactose. And this is L-galactose, as we know this is the L configuration. All right, so there's going to be 2 more of these. All right, back to more carbohydrates. So this one we are actually starting with the Haworth projection here. So let's first number these carbons, 1, 2, 3, 4, 5, and this is carbon 6 here. All right, so we're kind of going in reverse, but let's just first name this sugar. So this is idose. This is not a sugar I think you have to know for 271, but we can still see that the anomer here is, so the OH on carbon 1 and the CH2OH, these are opposite. So we know this is the alpha anomer, right? And we know the CH2OH is going down, so this is an L sugar. And we know this is a pyranose, right? So we have a nice 6-membered ring here. So this is idopyranose. And now we are trying to draw L-idose. So we're trying to get back to the Fischer projection now. So this is going the opposite. So let's draw our normal sort of structure for this, as we've been seeing. CH2OH. And draw 1, 2, 3, 4. All right. So numbering these 1, 2, 3, 4, 5, 6. All right. So looking at this, we know this is the L configuration, the L enantiomer. So that means that carbon 5 has to be on the left, right? So OH, H, right? So, and we got that from knowing that this carbon 6, the CH2OH, is down. So this tells us that this is the L, okay? And L has to have the OH on C5 on the left. For these other ones, so what we do is we know that carbon 2, carbon 3, carbon 4, so this carbon 2 is going down. So now we kind of look at the opposite. So this one is going to be on the right in the Fischer. So this one's going up on carbon 3, up is left. And then carbon 4, this is going down, so down is right. So what we see, carbon 2, the OH is on the right. Carbon 3, the OH is on the left. Carbon 4, the OH is on the right. That looks good. So that should be it for L-idose. It's fairly straightforward going in the opposite direction. You just use the reverse of these 2 rules. And then it's the same, just going in reverse using these two. All right, the next one. So this one's a little different because for this one we have CO in the middle. So this is going to be actually a 5-membered ring. Why? Because the OH here on this carbon, so this is carbon 5 still, the OH is going to attack this CO instead of the CO on carbon 1 like here. So normally what happens is this does a nucleophilic attack up here, and that's what forms the 6-membered ring with the O. But in this case, it's going to be a 5-membered ring because this one is going to attack this instead. Okay? So it's going to give us a 5-membered ring. This is called a furanose, not a pyranose. So still 6 carbons, but a 5-membered ring instead. Okay? But we follow the same rules. So this is carbon 3, carbon 4. So carbon 2 doesn't matter anymore because carbon 2 is the the carbonyl. But we can still look at carbon 3 and 4 with row 1. So carbon 3, this is on the left, this is going up. Carbon 4, this is on the right, this is going down. Okay? And then carbon 5, we see the OH is on the right, so we know this is a D sugar. All right? So how we draw the 5-membered ring is we draw the oxygen at the top, we draw a pentagon this time. Okay? And the main difference here is that on this carbon, carbon 1, carbon 2, 3, 4, like this. Sorry, this is actually wrong. So carbon 1 in this case is going to be this CH2OH. So this will actually be coming off of this carbon. So this is 2, 3, 4, 5. My bad. Okay, so on carbon 2 we will have both an OH and a CH2OH. All right, so let's first start out with carbon 5 here. So we know this is a D sugar. D sugar, this will be going up. So CH2OH going up. What I forgot to write is that this is going to be the beta anomer. So the beta anomer, we know the OH is going to be on the same side as the CH2OH on coming off of carbon 5, or carbon 6 here. So the CH2OH is carbon 6, but it is attached to carbon 5. So in this case, the OH will be here on the same side because this is beta. Right? Beta equals same side. And what that means is that if the OH is on the same side as the CH2OH on carbon 5, then the CH2OH on carbon 2 has to be pointing down. Right? Because the OH has to be going up, because it's the beta anomer, these two have to be on the same side, so therefore the CH2OH is on the opposite side, right? In order to match the specificity of the OH for the beta anomer. All right, so now for carbon 3, we know this one's going up, and for carbon 4, this one's going down. And that is it. So naming this is D-fructose. So this is from glycolysis. Very important sugar. And then this one is beta D-fructofuranose. And it's a furanose, unlike this, which is a pyranose, because this is a 5-membered ring. And that will be it for this lesson. Thank you.